This is explainable AI for plant disease diagnosis instead of these plants. That is from Makerere University. Uh, Makerere University. Next slide, please. This is the team. The team includes Samuel Tiwa, as you see, as follows. The background of our study, we are focusing on the maize crop, which is a maize staple crop, and it is eaten in most it is eaten in most places like schools, prisons, hospitals, and everyone eats maize, and it is also used in different as a food crop for different animals like chicken, that is maize brand. So it is a source of income for small scale farmers in developing countries, and in East African region. There was a combined production of 17.2 million tons in 2016. So the maize market plays a major role in the well-being of people in the East African region. Uh, as we see here, as the maize production has increased, so has the prevalence of diseases. So you can see that the example of disease like you see in the picture 3, picture 4, picture 5. But in this study, we are focusing on the menstruation disease, which is mostly a grass. It's a viral disease for maize, and also maize leaf blight, which is the fungal disease for maize. So so this affects the production of maize crops in the region. So our problem statement is that this research focuses on addressing the problem of the rise of maize disease in East Africa, especially the maize streak virus and the maize leaf. The aims to develop actually interpretable AI-based diagnosis using pseudo AI and deep learning techniques by by improving disease detection and the management. This research contributes to enhancing the maize productivity and global food security. So rated works, to go on the rated works, asking to work the model that was suggested, and this one's identifying maize leaf may was identifying maize leaf diseases using neural networks, and it involved what they call early stopping and transfer learning. But the model demonstrated an accuracy of 85%, 85.22%. To make the model accessible, the model was different to different people. So that is part of valid work that we are building on in this research. Uh, Someone, my colleague is going to take on.
Thank you, Sam. I'm Akeno Benedict Tanis, and I'm going to talk about our research questions. These research questions were basically answered throughout the entire course study. The first one was, how can we develop rate models to identify and categorize maize virus and leaf blight diseases using a data set of maize leaf images? And so here, basically, we want to develop mainly 3 models, which are the custom-made model, the VGG19, and the third one was MobileNet V2. Our second research question was, which model performs best in identifying and categorizing diseases, which were basically these diseases were maize leaf blight and maize streak virus, using advanced image recognition, where Now, we basically utilized ResNet 50 and PTG19 models. Our third question was, how can explainable AI techniques, for example, the use of SHARP, Live, LRP, basically help our users to identify, to understand the decision-making process of the chosen model out of the three models. Our fourth question was, how can we effectively deploy our model and mobile application using basically software tools like TensorFlow and Java, and also create a dashboard to provide explainability to our users. Next slide, please. These were our research objectives, which are derived from our research questions. And our ultimate goal was to perform explanatory data analysis on the given Maize dataset, and also create, train an image classification model from scratch, as well as create two pre-trained models, which are ResNet PT and PTG19. Our other specific objectives were, the first one, evaluate the three models and identify the best performing models out of the three models. Here, we basically evaluated our best performing models using evaluation matrices, for example, recall accuracy, F1 score, AUC, and choose our best performing model. Our next objective was analyze the best performing black box model and explain how it was able to make predictions using XAI tools, techniques, for example, use of SHARP and Live. Our last specific objective was deploy the machine learning model on a mobile application using TensorFlow Lite and React Native, Java, and also develop a web-based application using Django framework to serve as a dashboard for our data collected in the database. My colleague is going to talk about our methodology.
Thank you very much. Starting with our methodology, this is the outline of the methodology that we had proposed. First of all, we collected some data set. It acted as our baseline data set that involved over 15,000 images. And with these images, we were able to clean them, analyze them, and also pre-process them so that they into a tensor format that can be used to train models. So this diagram shows all the processes that we carried out in order to train our models and also to design our systems. So from here you can see that we started with image augmentation, where we basically duplicated our data so that we can enlarge on our data set, because initially we had like 15,000 images, but with the different data augmentation techniques that are provided by Keras, we want to increase this to about 90,000. Then we carried out classification. Now here we used different types of models. We used the custom model, and then we used the mobile net and also VGG19. And after that, we evaluated the model using the different evaluation matrices, the accuracy, the precision, the confusion matrix, and also we're able to identify the best performing model. Now, on the part of explainability, we were able to analyze the best performing model and also another model to see how we're able to come up with their predictions, to understand the reasoning behind their predictions. So we're able to do that, though we can still do more work about that. So we also designed an API using Flask, where the API contains our best performing model. So the user, we created a system that uses a mobile application where a user or an extension worker is able to send a diagnosis request. He puts in an image, then he sends it to the endpoint of our API. Then the model is able to return the predicted results and the accuracy, and also the diagnosis and also the treatment recommendations. So the next slide, please. This is just here we're just talking about model explainability, but most of this was discussed in our proposal. We were trying to understand what exactly is model explainability. Now, as you can see that most of the traditional maize disease diagnosis mainly relied on experts, whereby the government would workers to different regions, villages across the country, especially here in Uganda. And these extension workers were heavily relied on in helping farmers diagnose the diseases of their plants. And of course, this kind of method was subjective to so many inaccuracies, because there were times certain farmers couldn't receive extension workers because there were very few. Could find like there is a single extension worker in a village, or if at all there were extension workers, still they will have issues in diagnosing maize diseases. For example, because mostly they were using their visual inspection and knowledge. So this would really be challenging, especially in areas where they're not sure about the kind of disease, and they would want to carry out more research. So having such a tool would really help such people in farmers, but also the extension workers in easing their work in the diagnosis. Because remember, if these diseases are be easier to treat them and also to prevent different losses that come with them. Now, of course, there were limitations, because in our research study we are employing deep learning models. Now we know deep learning models are really accurate models, but then there are limitations to these models. Yes, they provide good accuracy, but still they are referred to as black box models. They don't provide an explanation to how they reached their predictions, and this would really be crucial to our stakeholders, the farmers and extension workers, who would want to really know whether such a system is really reliable. So that's why we come in with the explainable framework for the diagnosis of these plant diseases. Yeah, can you go to the next slide, please? Now, in our study, so this is the baseline data set that we had over 15,000 images, of which 5,000 were healthy, 5,000 had maize strep virus, and over 5,000 had maize it would not be a good representation, so there would be issues in the quality of our model. So in that, out to experiments, one with the augmented data and the other with the data. But we included in another score other than related images that in the augmented data. So can you go to the next slide, please? Yeah, so this is that we used for for our research. So you can see that in images that are unrelated to maize, then we have the MLB, we have the healthy, and also the analyze with exact mixed up. Able to proceed. First of all, we divided our data into different classes, starting with the augmented data, 3 classes: the training, validation, and testing. Now, training contained, you can see that the classes were kind of balanced from this graph. And also for the second data set that contained a fourth class, but the model doesn't can you go to the next slide, please? Yeah, so with our model training, we carried out 2 experiments. Since we were also so with the first experiment custom model, the VGG19 had an input size, an image input size of 224. Now this is the default that was defined when they were training the original VGG, and there would be no changing it because it's already embedded in the system. And also mobile had the same image custom model. We were able to reduce down the size so that model is able to pick on the number of network like VGG19 had over 20 neurons, then MobileNet had over 3 million, and the custom model. Second experiment, the input size, the image input size that changed were the network parameters, and this was because the images were different, and when we were carrying out the different experiments, we were to find out which network parameters were kind of different. So with VGG, we have 20 million still, but it's slightly bigger than the first one. Then MobileNet had 3.573 million. Model had the for the first experiment, which had only 1.1 million per. Now this was because for the high, that's why you're seeing the network, please. Yeah, so these were the model results that we're able to obtain starting with experiment 2. I actually had quite a good accuracy. This was the MobileNet, which had 0.99 accuracy, meaning really. And when you look at its confusion matrix, you can see that it number of mispredictions. For example, when you look at when you look at this part of others, the class was others, but then it diagonized it as healthy. So there was only one in VGG19 for that particular others class. It had over 5 images. And then when you look at when you look at VGG19, you can see for example, in the class of Maize virus, it had like 15 images that were misclassified, and yet for MobileNet it had none. Then for the forming model for the second data set. Yeah, next slide, please. Next slide, please. So these are the different graphs. that showcase the different model accuracy and loss, the validation and training accuracy and loss. Yeah. So next slide. Yeah, so these are also the graphs for experiment one. Yeah, next slide, please. Yeah, from that we were able to pick MobileNet as the best performing model. Then after we carried out some model explainability, we used two frameworks, the Sharp-Defect Explainer and Lime. With the Sharp-Defect Explainer, we try to analyze the custom model to see why it wasn't performing well as compared to the other models. So here we gave it an image which was basically metric virus, but it was able to diagnose it well. But from here it gave with the Sharp-Defect Explainer, we were able to get some insight into how the model was. Where you see the red spots, those were the features that the model used to see whether the image had the leaf had a disease or not. So from the first mask that we do, you can see that there were so many dots around the margin. And you can see from the original image, you can see that part was white, meaning that it had a streak. You can see that the model was able to see all this. Yeah, so let's go to line. Now, Lime, we tested it with another model, and here we were just a number of features and also changing the different values to see whether was better predictions on the goal that was. You can see that for each and draw around the red where we have the yellow and the green patches of our mask. You can see that those parts are they're kind of dry, meaning that they have a streak. Then with the custom model was misclassifying when we tested it with Lime. You can see that it was drawing masks in soil. For example, in this second image down here, it was drawing masks in soil, then around the margin, and also in some green parts. So maybe this could provide us insights into how we can actually debug our model and ensure that it checks out only the real feature, maybe also reducing the image to only the features that we see. Yeah, next slide. So after that, we were able to deploy our model. We used Java, which is Android, which provided us with the Android mobile development. So these are the screens for our mobile app. With the screens, the user is allowed to take an image, and then using the API that we designed in the background, the first API, the image is processed, and then the results are returned and displayed. And also we provide expert device. Now later on, the expert device, we shall modify it so that we use one of the large language models, maybe like ChatGPT, to provide insights. So now the leaf can be treated. But this expert device, we were able to get it from the different agricultural experts that we met. So these are some of the expert device that that the users can use in treating their diseases. The next slide, please. And also the user is given an option of saving the image, and this image is saved to our database together with the latitude, the longitude, and also the timestamp, so that later on we are able to determine how the diseases are distributed all over the East African region. Yes, I'll let in my colleague come and explain the next part.
Yes, thank you, Mr. Mbarak. In conclusion, the developed intelligence system was able to accurately diagnose the maize streak and leaf blight diseases. And secondly, the use of the AI techniques provided a clear understanding of the model decision making and providing insights for the black box models. Then thirdly, the deployment of the explained model on the mobile app increased accessibility and usability for users, allowing for real-time guidance on the disease management as shown by the previous presenter. Then, however, we had some limitations, and the first limitation was the performance of the model may be affected by the variation in the quality and resolution of the images used for training. If the images are not clear enough, that means the machine learning algorithms won't be able to detect the patterns clearly. Then secondly, the effectiveness of the model may be limited by the availability and diversity of the data set. And this is the reason as to why we tried out some data augmentation to increase the number of images in the model so that our model can learn very well the patterns there. Then further research may be necessary to address these limitations and improve the robustness of the system. For our future directions, we hope to expand the study to include, firstly, we hope to include other types of diseases affecting the maize plants, such as rust and fusarium wilt. Secondly, we hope to incorporate additional data sources. We are considering integrating weather data or information on crop management practices into the study. This is so, like, for instance, for our project, we're able to, on the user of the app, on scanning the image of the target leaf, we are able to track where the coordinates of the place of where the image was taken, and also the particular time. So with that data, we can be able to determine the weather of that particular place at that particular time. Then thirdly, we hope to collaborate with agriculture experts so that they can provide us with expert advice so as to improve our research in the field of agriculture. Then fourthly, we hope to explore integration with existing farming systems, investigate potential for integrating the disease diagnosis model with the existing farming management systems. For our references, we happen to visit a research paper authored by Erica, Lucas Daroca, Larissa Rodriguez, and Joao Fernando Mari. The research paper was entitled Maize Leaf Disease Classification Using Convolutional Neural Networks and Hyperparameter Optimization. Then, as we conclude, we would like to express our sincere gratitude to Dr. Joyce Naben, the head of the Macquarie AI Lab, for granting us permission to the Maize dataset. We also like to commend and applaud our supervisor, Mr. Galiwanga Marvin, for his unwavering dedication and guidance in helping us throughout the implementation and report presentation. Thank you so much. That was our presentation, Group 6.